Hi, I am Sanjay Patel. In this video, we are going to discuss some properties of beta functions. We have already defined what is a beta function. Let us recall the definition of beta function. Beta function is defined for say m and n, where m and n are positive. It's a function of two arguments, and it is defined as integral 0 to 1 x raised to m minus 1 into 1 minus x raised to n minus 1 dx. So just remember this definition of beta function, and we know this integral exists if both m and n are positive. So we define beta functions for all m and n greater than 0, where m and n are real numbers. Let us begin with the results or properties, which are theorems on beta functions. And this, I'm starting with the first one. Prove that beta m comma n is equal to beta n comma m for all m and n. Here, whenever I write for all m and n, means any two positive real numbers. That is, we can say beta function is symmetric. That is, beta function is symmetric in its argument. Is symmetric in its arguments. So whether you find beta of say m comma n or beta of n comma n, you will get the same value. Let us prove. We know that the beta m comma n is equal to integral 0 to 1 x raised to m minus 1 into 1 minus x raised to n minus 1 dx. That is our definition of beta function. Let me take some substitution to prove the result. I will replace 1 minus x by some other variable. So let 1 minus x is equal to t, and whenever we take a substitution in definite integral, we must change the limits of integration as well as the differential and all the variables in terms of the new parameter or the new variable. So first of all, let me write dt, that is equal to minus dx. Okay, differentiating both the sides. Also, when say x is equal to 0, from this relation, when x equal to 0, I can say t is equal to 1. T is equal to 1. And when x is equal to 1, we have t equal to 0. So putting these values in the right hand side of this beta function formula, what we get is beta m comma n is equal to integral, say when x equal to 0, t is equal to 1. So the new limit is 1, and when x equal to 1, t equal to 0. So putting these two values and replacing x, where 1 minus x is t, we have x is equal to 1 minus t. So this is 1 minus t raised to m minus 1. 1 minus x is t, so t raised to n minus 1. And dx is minus dt. Because dt is equal to minus dx, so I can replace dx by minus dt from this result. And integral a to b is same as minus 1 times integral b to a. So interchanging the limits, I can remove this minus sign and write integral 0 to 1 t raised to n minus 1. This I am writing first, then into 1 minus t raised to m minus 1 into dt. This minus sign is replaced by changing the this limits of integration. What is this right hand side? This thing is actually the beta function at n comma m in this reverse order. So I can write this is same as, this is same as beta of n comma m. So the result is proved. Beta mn is equal to beta n comma m. So beta m comma n is equal to beta n comma n. Let us prove the second result, which is very, very simple. So the second result is prove that beta m comma n is equal to beta m plus 1 comma n plus beta of m comma n plus 1. Okay. For this, I will start with the right hand side of this result. So consider RHS, that is beta of m plus 1 comma n plus beta of m comma n plus 1. Okay, this I can write as by definition of beta function, it is integral 0 to 1. We have x raised to say m minus 1. This is your m plus 1, so it will be m by definition into 1 minus x raised to n minus 1, correct? Dx plus this thing is integral 0 to 1 x raised to m minus 1 into 1 minus x raised to n dx. So we have integral 0 to 1 of one function plus integral 0 to 1 of some other function. So using the working rules of integration, this I can write as integral 0 to 1 x raised to m into 1 minus x raised to n minus 1 plus x raised to m minus 1 into 1 minus x raised to n dx. Okay. Now from this expression, you can see that I can take something common. So taking integral 0 to 1, taking the minimum value or minimum power of the two different types of terms x and 1 minus x as a common factor. So I am writing x raised to m minus 1, so minimum of m and m minus 1 here, and 1 minus x raised to n minus 1. What is left inside the bracket is x raised to m is m minus 1 is taken common, so I should write x here in order to have the same expression, and here x 1 minus x raised to n minus 1 is taken common, so still 1 minus x will be left, this into dx, and this is equal to integral 0 to 1 x raised to m minus 1 into 1 minus x raised to n minus 1. This is nothing but 1. So this will be cancelled and you will get simply 1. So this gives you, let me write dx here, this gives you beta of m comma n, which is equal to your LHS. So we have proved that LHS is equal to RHS in this result. This was the requirement. Let us go to the next property, number 3. Property number 3 is very, very important and very, very useful. Prove that beta m comma n is equal to 2 times integral 0 to pi by 2 cos raised to 2m minus 1 theta into sine raised to 2n minus 1 theta d theta. Okay, so we want to prove this result. So we start with the definition of beta function. We have the beta function formula beta m comma n, which is equal to integral 0 to 1 x raised to m minus 1 into 1 minus x raised to n minus 1 dx. This is our definition of beta function. To convert into this trigonometric integral, let us substitute something for x. So I am changing the variable. Let the x is equal to say cos square theta. Let's take x is equal to cos square theta. So this implies I will get dx is equal to 2 cos theta, and derivative of cos theta is minus sine theta. So I am writing that minus sign here into d theta. Okay, and also when we have the lower limit x equal to 0, the corresponding value of theta you can get is theta is equal to pi by 2. Okay, because x is equal to cos square theta, you can put x equal to 0 over here, you will get cos square theta is equal to 0. That means cos theta is 0, and therefore theta is pi by 2. And when x is equal to say x is equal to 1, the upper limit of integration, when x is equal to 1, we get cos square theta is equal to 1, and taking the positive value, we'll get theta is equal to 0. Okay, for x equal to 1, we get theta is equal to 0, taking the positive square root. So putting all these values in that above formula of a beta function, we get beta m comma n is equal to integral. Now for x equal to 0, corresponding value of limit is theta is equal to pi by 2. So here I should write pi by 2. For x equal to 1, theta is equal to 0. X raised to m minus 1, you know that x raised to m minus 1. So x is cos square theta, so I must write cos square theta raised to m minus 1 into 1 minus cos square theta raised to n minus 1, and dx is minus 2 cos theta into sine theta, let me write in the bracket, d theta. Okay, let us simplify this. This is equal to taking this minus sign outside of this integral and then replacing or interchanging the limits of integration, I can make it positive. So this is equal to integral 0 to pi by 2, integral 0 to pi by 2, this is cos raised to 2m minus 2 theta. Okay, 1 minus cos square theta is sine square theta, and sine square theta raised to n minus 1 gives you sine raised to 2n minus 2 theta, and into there is a 2 cos theta sine theta, so that 2 I am writing here, and into cos theta into sine theta. Okay, and into d theta is also there. Now just simplifying this, you will get your required result. This is equal to 2 times integral 0 to pi by 2. This is cos raised to 2m minus 2 and cos theta, that gives cos raised to 2m minus 1. So cos raised to 2m minus 1 theta, same way sine raised to 2n minus 1 theta d theta. Hence the result is proved. This was our aim. Beta mn is equal to 2 times 0 to pi by 2 cos raised to 2m minus 1 theta into sine raised to 2n minus 1 theta d theta. So this is very, very important say formula for beta function. All these are useful in computation of beta and gamma functions and solving some important problems. Let us go to the next one. So problem number 4, or rather result number 4, property number 4, that I would like to prove another useful result for computation, and it is again for a beta function, as prove that integral 0 to pi by 2, say sine raised to p theta into cos raised to q theta d theta is equal to 1 by 2 times beta of p plus 1 by 2 comma q plus 1 by 2. So again another useful result, and the proof of this is very simple. It follows from the previous result, means the result number 3. So we know that beta m comma n is equal to 2 times integral 0 to pi by 2 cos raised to 2m minus 1 theta into sine raised to 2n minus 1 theta d theta. This is I am writing from result 3 or the property number 3. In this result, you just observe we want sine raised to p here, and we have 2n minus 1 is equal to p. I mean 2n minus 1 power of sine. So what I will do is, let us put say 2n minus 1 is equal to p. So I will get sine raised to p term here, and 2m minus 1, this number I am calling as q. As a result of this, what you will get as m and n is m is equal to, say, let me write n first because you can understand easily. So n is equal to, say, p plus 1 by 2, and from this we will get m is equal to q plus 1 by 2. So putting all these values in this above result, we get beta of m is q plus 1 by 2 and n is p plus 1 by 2 is equal to 2 times integral 0 to pi by 2 cos raised to q theta into sine raised to p theta d theta, because 2m minus 1 is 2m minus 1 is q, and 2n minus 1 is p. Okay, 2n minus 1 is p. Dividing by 2 and using that fact that beta is symmetric function, its argument, I can rewrite this as 1 by 2 times beta of p plus 1 by 2 q plus 1 by 2, because beta of x comma y is same as beta of y comma x. This is equal to integral 0 to pi by 2 sine raised to p theta into cos raised to q theta d theta. So this is another very useful result for beta function. So if you are given this kind of integral, and if you want to find the value of this integral, you can directly use the beta function using this formula. And result number 3 says, if you have a beta function, you can convert it into this type of integral involving trigonometric function in for easy computation. So let us go to the next one, number 5. So result number 5 is this. Prove that beta m comma n is equal to integral 0 to infinity x raised to m minus 1 upon 1 plus x raised to m plus n dx. So this is the formula of beta function in terms of this kind of limits 0 to infinity. Let us prove this. Okay. So I start in this way. we have beta of m comma n same as beta of n comma m by result number 1. It is symmetric. And beta of n comma m, by definition, I can write this as integral 0 to 1 x raised to n minus 1 into 1 minus x raised to m minus 1 dx. Okay. Now to get this right hand side, this x raised to m minus 1 upon 1 plus x raised to m plus n, I must take some substitution. So let me choose some proper substitution. Let us take say x is equal to 1 upon 1 plus y, say. As a result of this, what I will get is dx is equal to minus 1 upon 1 plus y whole square into dy. Okay, so dx will be replaced by this. Further, about limits of integration, I can say when x is equal to 0 and x equal to 0, what is the value of y? That you can calculate from this. If you put x equal to 0, 1 upon y, 1 upon 1 plus y becomes 0. And that is 1 upon 1 plus y reciprocal is 0 only if 1 plus y is infinity. That means y must be infinity. And when x is equal to 1, putting 1 here, we get 1 upon 1 plus y is 1. That means 1 plus y is 1 and hence y equal to 0. So these values of limits, new limits, you can calculate using this relation between x and y. So putting this all values in result number 1, what I will get is beta mn is equal to this thing. So we get beta mn from 1, we get beta of m comma n is equal to integral, say for 0 it is infinity, so infinity to 0 x, that is 1 upon 1 plus y, x is to n minus 1 is there, so it is 1 upon 1 plus y raised to n minus 1 into 1 minus x. So what is 1 minus x here? That is 1 minus 1 upon 1 plus y raised to m minus 1, and dx is nothing but minus 1 upon 1 plus y whole square into dy. Okay, just putting this value. Let us simplify this. Take this minus sign here and we use it to make this change of this upper and lower limit, interchanging upper and lower limit. I can write 0 to infinity. This is 1 upon 1 plus y raised to n minus 1. Okay. This is nothing but again 1 upon 1. It is 1 plus y minus 1 upon 1 plus y. So that is nothing but y upon 1 plus y raised to m minus 1 into 1 upon 1 plus y square dy. Just note that I have removed this minus sign, and that is used here to interchange these limits, because you know integral a to b is same as minus 1 times integral b to a. So this I can write as, by simplifying, integral 0 to infinity, see y raised to m minus 1, upon, this is 1 plus y raised to n minus 1, this is 1 plus y raised to m minus 1, and this is 1 plus y raised to 2. So all adding, what we'll get is n minus 1 plus m minus 1 and 2. So 2 will get cancelled, and finally if you verify you will get m plus n into dy. Okay, it is very simple. N minus 1 and this is m minus 1. So m plus n minus 2 and this is 2. So 2 gets cancelled and you will get only m plus n. And replacing this variable y by x, we get the required result. So this is equal to integral 0 to infinity x raised to m minus 1 upon 1 plus x raised to m plus n dx. What we have done is not any substitution but just replacing the dummy variable y by x, and this is our required result. So we have proved that beta mn equal to x raised to m minus 1 upon 1 plus x raised to m plus n integral 0 to infinity. Okay, so hence the result is proved. Hence the theorem is proved. We are going to prove one more result of this type. I think it is next number, what, 6, yes. So let us prove the result number 6 next. Prove that integral 0 to 1 x raised to m minus 1, let me write properly, integral 0 to 1 x raised to m minus 1 plus x raised to n minus 1 upon 1 plus x raised to m plus n dx is equal to beta m comma n. Okay. To prove this, let us start with the left hand side. Proof of this result. So consider the LHS, that is integral 0 to 1 x raised to m minus 1 plus x raised to n minus 1 upon 1 plus x raised to m plus n dx. Separating this, we will get integral 0 to 1 x raised to m minus 1 upon 1 plus x raised to m plus n. Let me write like this, plus x raised to n minus 1 upon 1 plus x raised to m plus n. So a plus b upon c is equal to a upon c plus b upon c into dx. This I can separate using the working rules. Integration of fx plus gx is equal to integral fx plus integral gx. So this I can add as integral 0 to 1 x raised to m minus 1 upon 1 plus x raised to m plus n dx plus integral 0 to 1 x raised to n minus 1 upon 1 plus x raised to m plus n dx. And I will compute both these integrals separately and then add them, and finally we'll get the required result, that is beta function. Our aim is to prove that this thing is equal to beta mn. This thing is equal to beta mn. So I will try to prove that the sum of these two is nothing but the beta function. So let me call this as I1 and this integral as I2, and let me name this as result number 1. Okay. So first part, start with I1. Now I1 is integral 0 to 1 x raised to m minus 1 upon 1 plus x raised to m plus n dx. Just keep in mind that I2 is also a similar thing, that is x raised to n minus 1. Only one change is there in I2. Instead of m minus 1, we have n minus 1 here. Just keep that in mind. This I want to change into new variables by taking a substitution like this. So let us take, say, x is equal to, say, z upon 1 minus z, z upon 1 minus z as a substitution. Okay. Then this I can write as by adding and subtracting 1 in the numerator, I can add x is equal to 1 minus 1 plus z upon 1 minus z. Okay, add and subtract 1 here. Then I can rewrite this as 1 minus z upon 1 minus z. Just to make the computation simple, I am taking this step. Now again, a plus b upon c is a upon c plus b upon c. So I can write this as 1 upon 1 minus z, and this 1 minus z will be cancelled, so it is minus 1. So we have another, say, expression for the substitution for x. Okay. And from this I can compute the differential dx easily. So therefore dx will be derivative of x, then differentiating both the sides, it is minus 1 upon 1 minus z square, and then derivative of 1 minus z is minus 1, so this will become plus 1. Okay, this will become plus 1, and into dz is also there. What we are going to do is we are going to change this integral in terms of this new variable. So this is the change of variables here. So everywhere x appears, we substitute this, and this dx will be replaced by this thing, 1 upon 1 minus z square into dz. And now limits of integration. When x equal to 0, what happens to z? So just note that when x is equal to 0 and when x equal to 1, what is the value of z? When x equal to 0, you can put, say, 0 here. So what you will get, 0 is equal to 1 upon 1 minus z minus 1. So 1 upon 1 minus z is minus, that is plus 1. So z is, in this case, 0. Yes. Okay. You understand? See, putting x equal to 0 here in this, I will get 0 is equal to 1 upon 1 minus z minus 1. That gives me 1 upon 1 minus z is equal to 1, and taking reciprocal 1 minus z is equal to 1, and that gives me z is equal to 0. Okay, so same way, let me remove this, which is not required. Same way for x equal to 1, when x is equal to 1 here, that 1 will be cancelled, and you will get 1 upon 1 minus z is equal to 0, and therefore 1 minus z is equal to, just 1 minute, when x is equal to 1, okay, it is not 0, when you put x is equal to 1 here, so you will get 1 upon 1 minus z minus 1, so that gives you 2 is equal to 1 upon 1 minus z. Okay, and that gives you 1 minus z is equal to 1 by 2, taking reciprocal both the sides. So z is equal to 1 minus 1 by 2, which is nothing but 1 by 2. So when x equal to 1, we have z is equal to 1 by 2. Okay, now putting all these values in that integral, the beta function, that is I1, I can write I1 is equal to, remember this, so therefore I1 is equal to integral 0 to 1 by 2, and we have x there. What I have written as x is to m minus 1. So let me write first this original integral so that we can put the values very easily. Integral 0 to 1 x raised to m minus 1 upon 1 plus x raised to m plus n dx. So this is equal to integral, for x equal to 0, z is equal to 0. So this is 0. For x equal to 1, z is equal to 1 by 2. So corresponding value of the limit is 1 by 2. X is our substitution, which is z upon 1 minus z upon 1 minus z, z upon 1 minus z, and this raised to m minus 1. Okay, this raised to m minus 1 into 1 plus x. Now what is 1 plus x? That you can get from this. X is equal to this thing, so 1 plus x is 1 upon 1 minus z. Okay, so that is 1 upon, let me write this way. From this, you will also get 1 plus x is equal to 1 upon 1 minus z. Okay, so 1 upon 1 plus x is 1 minus z simply. So I must write 1 upon 1 plus x is replaced by 1 minus z raised to m plus n, and dx is replaced by 1 upon 1 minus z square dz. It is this differential, this one. So I am putting this value in place of dx. Okay, remember I replace that 1 upon 1 plus x by 1 minus z. Now simplifying further, this we will get as 0 to 1 by 2. There is only one z term, so it is z raised to m minus 1. Okay, z raised to m minus 1. And simplifying this, 1 minus z raised to m plus n. This is upon 1 minus 1 upon 1 minus z raised to m minus 1. That becomes, say, minus m plus 1, and this becomes minus 2 into dz. So what will happen is, simplifying, m will be cancelled, and n minus n plus 1 minus 2, that gives you n minus 1. So this is nothing but integral 0 to 1 by 2 z raised to m minus 1 into 1 minus z raised to n minus 1 dz. What I have proved is I1 is equal to this. Let me call this as result number 2. Okay, what I am going to do is I'll put all these values here in result 1. Okay, now consider I2. We have I2 is equal to integral 0 to what was that? We have I2 is equal to, I think, integral, yes, 0 to 1 x is to n minus 1, 0 to 1 x is to n minus 1 upon 1 plus x raised to m plus n dx. Okay, this I can write directly as we have discussed this result 2. We have derived result 2. I can write directly this as integral 0 to 1, rather 0 to 1 by 2. This is equal to 0 to 1 by 2, then z raised to say n minus 1, z raised to n minus 1 into 1 minus z raised to m minus 1. So it is a similar thing, just interchanging the roles of m and n. This is another thing. This I can write from because of result 2. Okay, by result 2. It's a similar thing. Further, I want to change this integral by taking a substitution, new substitution here. So let me take 1 minus z is equal to, say, t. So that gives us dt is equal to minus dz. And also the limits of integration will change. When z is equal to 0, I will get t is equal to 1. And when z is equal to 1 by 2, I will get t is equal to 1 by 2, just from this. And putting all these values in this tab, let me call it star. So therefore, star implies I will get I2 is equal to integral for 0, it is 1. So it is 1 to 1 by 2, z is 1 minus t raised to n minus 1, and 1 minus z is t, so t raised to m minus 1, and dz is minus dt. Just putting all these values in this integral, this star, we will get this expression for I2. This I2 I can rewrite as integral 1 by 2 to 1 by removing this negative sign, t raised to m minus 1 into 1 minus t raised to n minus 1 dt. Correct? Which I say again, just replacing the dummy variable t here, I can rewrite this as 1 by 2 to 1 z raised to m minus 1, 1 minus z raised to n minus 1 dt. What we have done is not a substitution now, it is just a replacement of say the variable t by the new variable z. Remember, in definite integral, the variable is not important, so you can replace anytime you want. So this is my I2. Okay, this is my I2. Let me call this as result number 3. So putting the value of result 2 and 3 in 1, this is 2, this is 3, sorry, this is 3, this is 2. Putting all this in our first result, which is we have started LHS is equal to, we get I1 plus I2. So just I have to add this two things, sorry. So adding I1 and I2, we get I1 plus I2 is equal to, I1 was integral say 0 to 1 by 2, 0 to 1 by 2, z raised to m minus 1, 1 minus z raised to n minus 1 dz. Okay, it is not dt here, this is dz. Okay, fine. Just look at that I1, z raised to n minus 1, 1 minus z raised to m minus 1. Okay, I have written the other way. Sorry. Okay. So what will happen here is, okay, here is also a small error. This 1 minus t raised to n minus 1 we have written. This is replaced by 1 by 2 to this, where t raised to m minus 1, and we'll get this. Okay, so z raised to n minus 1, fine. So yes, it is fine. So this is I1 plus I2 is 1 by 2 to 1 z raised to m minus 1 into 1 minus z raised to n minus 1 dz. Okay, it is here only. So just I put the value of result 1 and result 2 and result 3, and this is now something like integral a to b fx plus integral b to c fx dx. Okay, both the integrals are same, so I can combine these two integrals and write this as, this is equal to integral 0 to 1 z raised to m minus 1 into 1 minus z raised to n minus 1 dz. Just remember that I'm using this integral a to c fx plus integral c to b fx dx is equal to integral a to b fx dx. Okay. And what is this? This is nothing but the beta function. This is equal to beta of m comma n. Beta of m comma n. And that proves our required result. Putting this value in 1, substituting this in result number 1, we get that LHS, which was integral 0 to 1 x raised to m minus 1 plus x raised to n minus 1 upon 1 plus x raised to m plus n dx is equal to beta m comma n. So the result is proved. So these are some properties of say beta functions. In the previous video we have seen some properties of gamma functions, and now in the next lecture we are going to derive relationship between beta and gamma function, which is one of the most important result about gamma and beta functions. So till then, goodbye.